All right, welcome back. I'd like to talk to you about time domain signals. So you notice how we've been toying around a lot in the frequency domain or the phasor domain with our waves here. What I'd like to do now is just a quick review on how to think of this thing in terms of a time domain signal. Now, first, I'm going to do a little bit of mathematical rearrangement here. For starters, I'm just going to ignore the reverse propagating wave. We're just going to focus on the forward wave, and for simplicity, just neglect this guy. But the derivation is basically the same if you want to include it. Next, we're going to remind ourselves that this propagation constant, gamma, has a real and an imaginary component to it. Oops, sorry, it's alpha plus j beta. Okay, so this alpha here, remember, is the attenuation constant. And then the beta here has a number of names. Usually you can call it the phase constant, maybe. You can also call it the propagation constant is another word. These are often kind of given the same name. So that's the complex propagation constant. This is the propagation constant, but you can also call it the wave number, I suppose. And sometimes these names get used interchangeably with the gamma. So usually the context, you have to be careful. So in this sense, in this context, I'm just going to call it the phase constant, I suppose. But you can call it a wave number or the propagation constant as well. Because oftentimes we tend to do lossless systems anyway, where this guy is 0, and then these things essentially become synonymous anyway. So just remember there can be a little confusion between the names of these two things. So let's go ahead and write this out. I'm going to get the following. So remember, I'm ignoring this guy for now. And I'm going to get v naught plus e to the minus alpha z times e to the negative j beta z. Okay, so I just plugged in that term there. Now, this v naught, this amplitude, is technically a complex number, so it can have some phase information associated with it. So it's important to remember that v naught plus is actually some magnitude with a phase associated with it. So this is the polar form for that complex number, which means I can now rewrite my phasor as the following. The magnitude of v naught plus times e to the minus alpha z, e to the minus j beta z times e to the j phi. So that phi represents the phase on that amplitude there. So at the end of the day, all of this stuff, just remember, it's going to represent a wave that is kind of decaying to the right. All right, so the attenuation here determines how quickly it decays here. This phase term here is going to kind of determine the distance between the peaks and the troughs, and this little phase here is going to represent kind of an absolute shift in everything to the left or the right. And of course, we generally want waves to decay in this direction, right? Because you could hypothetically have a wave propagating that way, but then it's blowing up in amplitude, in which case you'd have an amplifying medium, but that generally doesn't happen in transmission line theory, so we tend to just ignore that case and pretend it doesn't exist. But it would actually qualify as a solution to this wave equation if you had the right characteristic parameters. But anyhow, so we're now back to this thing here. So notice this is just a rewrite of this expression up here, but it's still got all these complex numbers in it. So how do I treat that as a time domain signal? So the thing to remember is every phasor technically is a kind of a time-ish, domain-ish signal anyway, but by convention we just sort of ignored the t. So I'm going to write this as the following. So it's a phasor in the sense that it's complex, but it's going to have a function of time added to it. And I'm going to write it as simply v of z times e to the j omega t. So this little time domain, this time term here, is kind of implied. Like it's never really disappeared. It was always there. It's just that all of the operations we do on our signals in our analysis don't have anything to do with the actual frequency of excitation. So as a matter of convention, we just sort of cover this up and never actually write it down, even though it technically never went away. It was always there. So when we want to go back into the time domain, we just sort of explicitly write it out and say, oh yeah, by the way, this never went away. It was always here, so let's write it down. However, we're still using all these complex exponentials here, and I need to get rid of all my complex numbers somehow. So to go into the true time domain, v of z comma t, without the tilde, I'm just going to take the real part of this guy here, v of z e to the j omega t. So hopefully this is still review, but it's a good refresher to remind ourselves how all this stuff works. So you look at all these complex exponentials here. I'm just going to apply Euler's identity here. So I have v tilde of z is equal to, I'm just going to write all this out. Only every time I see a complex exponential, I'm going to put the cosine plus j sine term here. So v naught plus e to the minus alpha z. Now I'm going to get a big term here. So I'm going to have a cosine of the following. Oh, I need to include my timer, so that's okay. So I'm going to put a phi minus beta z plus j times the sine of phi minus beta z, like so. And then when I multiply also this j omega t term here, I'm going to get an omega t minus that and an omega t minus that in there as well. So let's write that down explicitly. V of z e to the j omega t. So if I were to multiply it up into here and carry it all through, I get the following. V naught plus e to the minus alpha z. So then it becomes cosine of omega t plus phi minus beta z minus j sine of omega t plus phi minus beta z, like that. Okay, so I'm just multiplying that guy in there, and then you apply Euler's identity, and you notice I'm getting my cosine term here, and then there's just this annoying sine term over here with the imaginary component kind of just hanging out. So the way we clean all that up is you just take the real part of it all, and so you imagine just sticking a little real here onto everything like that, and all it does is have the effect of throwing away that little annoying imaginary bit. So the end result is a true time domain signal where I get v of z comma t is equal to the magnitude e to the minus alpha, that's a z there, alpha z, and times the cosine of omega t plus phi minus beta z, like so. Okay, so at the end of the day, that's how we convert from a phasor signal, original phasor, right? So there's just magnitude and phase, but no time dependence. But really, the time dependence was kind of implied all along. So you do this little special operation here. So just remember, this is all you fundamentally have to do. So it's a very verbose way of saying, do this to get this down here. Okay, so from phasor to get the time domain version. And so you see you have the real part of your phase term here represents an exponential decay. Then I have my propagation constant here with my frequency. And then, of course, all the usual rules of sine waves start to apply after this, where I have a wavelength is equal to 2 pi over beta. And I also have a phase velocity that is omega over beta, which will also be lambda times my frequency. And of course, frequency is equal to 2 pi, or sorry, it's omega over 2 pi, like so. So usually I prefer to remember that omega is 2 pi times that. So that's called, there's frequency here, and then that's called the angular frequency there. So hopefully, again, this is all just review, but it's a very important thing that you'll have to do from time to time, where you start here and get this guy over here.